Hello physics students. In this video, we're going to be doing a lab called Determining the Permeability of Space Using a Long Wire. Now at this point, you should have already printed out pages 3 through 7, which include the data table, a graph, and places to do the data analysis and answer the questions. Printing out pages 1 and 2, the instructions, once again, is optional. You don't need to unless you feel it'd be more convenient for you to have a hard copy of these. Now, the basic expression for the magnetic field around a long wire is this formula, which we learned earlier in the topic. The magnetic field is equal to mu0, a constant, the current in the wire over 2 pi r, how far away you are from the wire. In this experiment, we're going to be determining this constant mu0. Of course, we know what it is, but we could look it up, but we're going to determine it experimentally. To do that, what we're going to be doing is we're going to be measuring the magnetic field at different distances from a long wire. And we're going to have a relationship, so we're going to have a bunch of data points, a radius, a magnetic field, a radius, magnetic field, right? And that'll create a data table that we can plot. And we can plot that, and you know the shape of this, because of the 1 over r relationship in the formula, will be a descending curve like this. What we're going to be doing is doing something to the one or both of the variables to produce a straight line graph, and somehow that slope is going to help us determine the mu0 in this equation. So the equipment we're going to be using, I've got set up here. This is my long wire. I don't know if you could see that, but it goes from this clamp to the clamp back there, and I'll be measuring the magnetic field in this general vicinity. So to explain how I'm going to make the measurements, I'm going to reconfigure the camera for a closer view. So here's my long wire that I'm going to use to generate a magnetic field. I'm going to use this sensor connected to this calculator to measure the magnetic field at different radii. To determine the radii, the distance I am from this wire, I have the wire resting on a ½ meter stick. I don't rest the wire at the 0 mark, because if I try to do that, it would just keep falling off the end of the meter stick. So I center it on the 10 centimeter mark. And then if I want to measure at 2 centimeters, obviously I'm going to put the sensor at 12 centimeters. Then 13, 14, 15 for 2, 3, 4, 5, so on and so forth, centimeters from the center of the wire. Now, because of the way this sensor works and the manufacturing process, it needs to be zeroed before I begin the experiment. What that means is I've got to put it into this 0 Gauss chamber, which creates a region of very near 0 magnetic field. And then I'm going to tell the software to note the general characteristics of the electrical characteristics of the sensor, and that reading at that point corresponds to 0 magnetic field. So I believe it's finished. Now if I begin the data collection, the sensor reading is pretty close to 0, fluctuating a little positive, a little negative, but around 0. If I pull this sensor out, what I suddenly see is that the reading is no longer 0. And the reason why is because the magnetic field at this point is not 0. As you no doubt know, the Earth itself creates a magnetic field. So humans discovered long ago, centuries before, that if you took an object with magnetic properties and allowed it to swivel on a frictionless surface, then it would always align itself in the same orientation at a certain part of the Earth. So if I displaced it this way, it would go back to this way. If I displaced it this way, it would go back to that way. Now, in the scale of the globe, what happened was, even if you were in the middle of the ocean, this would swivel this way. And so what humans did, because they did not really understand magnetism very well, they decided that since this end of this object pointed toward the geographic North Pole, they would label it north. And since this end was more or less aligned toward the South Pole, they would label it S for South Pole. So this is the North Pole, South Pole. But unfortunately, that means that since opposites attract in magnetism, if this is truly the North Pole of this object, that means it's attracted to up here this is the south pole, the magnetic south pole of the Earth. So the geographic North Pole is the magnetic South Pole, again, for historical reasons. Also, the true magnetic South is not up here. It's somewhere, I'm not exactly sure, I don't remember, it's somewhere in this vicinity. So this is the magnetic South Pole of the Earth. Now, we're in New York State over here, which is right here. And so our magnets point this way, but it turns out that there isn't just a magnetic field component that points this way. The Earth acts like a giant bar magnet, with the top of it being the South Pole, and this is the magnetic field around a bar magnet. And as you could see, the magnetic field points not only in a general upward direction toward the South Pole, but it also can point down into the object. So that's true of the magnetic field in this room. There's a component that points this way, but most of it actually goes down into the Earth. So if this were free to rotate on, in all the axes, it would point not just like this, but pretty much like this. Now we're going to need that direction for our experiment. So in order to determine the net direction of the Earth's magnetic field in this room, we're going to use this device, which is called a dip needle. So I'm going to reconfigure the camera so we could see the action of the dip needle, the way we can determine the direction of the net magnetic field in this room. So this dip needle has a swivel like this, and what I'm going to first do is I'm going to turn this so that it's as level as possible. So I'll just kind of maybe use the desk to see the level here, maybe a little bit more this way. And eventually the needle will settle. I'll help it settle so we don't have to just wait for it to oscillate on its low friction point. It'll settle in the direction of the horizontal component of the Earth's magnetic field, this way. So this is the magnetic north directly away from the camera. What I'm going to do now is turn this so that this axis is aligned with the needle, the compass needle here. So maybe I'll stand from above, a little bit more like this. So bear with me, I've got to really try and make some fine adjustments here. Okay, so now this is aligned with the horizontal component of the Earth's magnetic field. So this needle points directly away from your line of sight. The Earth's magnetic south pole is straight that way. Now what I'm going to do is move the camera 90 degrees to this and turn the dip needle so we can get the direction of the vertical. So again, the needle's aligned this way. And now when I turn like this and put this protractor in the vertical direction, I will be determining the direction of the net magnetic field of the Earth here at this point in this classroom. So now we've got to wait for it to sort of settle out. Maybe help it along a little bit. Okay, there it is. So I'm going to read that angle. Oh, I think my movement, my breathing, set it into motion a little bit. So here is the 180, which marks the vertical direction. And this is 10 degrees over. And I would say maybe a little bit more than 15 degrees. I guess the camera's in the way. When I move the camera, I'll get a more accurate measurement, but I would say maybe like 16 or 17 degrees away from the vertical. That's the angle. So most of the Earth's magnetic field goes down a little bit towards the north direction. Okay, so I'll move the camera and I'll get the more accurate reading. So the dip angle that I got was 17.5 degrees, which I recorded here. But as in every other experiment this year, you're not going to record this value. You're going to go into the Google Stream and find the sheet of data and get the dip angle assigned to you and record it in the data sheet here. So go ahead and do that now. Now, in order to minimize the errors in this experiment, the measurement errors, what I figured out is that it would be best if the maximum magnetic field recorded in this experiment was at least twice as large as the Earth's downward component of the magnetic field. The problem is that in order to create such a magnetic field, I would need about 10 amps of current. That's a little on the high side for this power supply. It can't really handle that. So what I figured out is that I could use this special kind of wire. It's used for sprinkler systems. And it may look like one wire, but it's actually, if you look here at the end, it's 7 wires. So there's 7 wires passing through here. What I've done is I put a connector on here so that when I connect it to this end of the wire, what it does is it makes the current spiral and go 7 times in the wire loop that I've established around the room. So any current that comes out of here is going to actually produce a net effect of 7 times the current of this going through this wire as it passes through each individual strand of the wire. So kind of a little clever way to boost up the amperage. Now, I'll plug this in and turn my ammeter on. And so what I'm going to do is get somewhere around 1.4 amps in the cable. Oops. Okay, so a little, maybe right around there, about 1.46 or 1.45 amps. Let's let it settle down a little bit. All right, 1.47 amps in this wire, but of course you have to multiply that by 7 and then record the resulting value here in the data table. So go ahead and look up the current in your in the Google sheet in the Google Stream, multiply it by 7 and record that value right here in the data table. So do that now. All right, so now that we have the current established, we're ready to start measuring the magnetic field at different radii. So let me reconfigure the camera. All right, so I have my current set up. I'm ready to start measuring the magnetic field. But one other point, the instructions say to pick the side of the wire where the magnetic field from the wire is in the same direction as the Earth's magnetic field. Now remember, the Earth's magnetic field has a downward component everywhere. The current in this wire is going this way. We would figure that out if we went back and inspected the power supply. So in order to find which way the magnetic field goes around the wire because of the current, I need this right-hand rule. What I do is I put my thumb in the direction of the current, and I see that my 4 fingers come up on this side of the wire. That means on this side of the wire, the magnetic field of the wire up is the opposite way of the Earth's magnetic field. So I don't want to make my measurements on this side. At the top here, the magnetic field goes basically toward your left. So the Earth's magnetic field goes this way, the wires goes this way, so we don't want to measure the magnetic field on the top. Over here, the Earth's magnetic field goes down, the wire's magnetic field goes down into these textbooks, and so does the Earth's magnetic field. So this is where I want to make my measurements on this side of the wire. So all right, next thing that I'm going to do is I'm going to take this sensor and put it at the various radii. If you look at the data table, you can see that the radii that I'm going to be using is 0.02 meters, in other words, 2 centimeters, 3, 4, 5, all the way up to 11 centimeters away. So I'm going to be measuring the magnetic field at all these points. What I want to do is when I put this at the proper radius, I don't want to put it all the way down, because then the tip of the magnetic field sensor, which is where it measures the magnetic field, will not be in the same plane as the center of this wire. So I want to hold it up a little bit, like a couple millimeters, so we're at the same plane of the center of the wire. And also, I don't want to be tilting it like this or like this. I want this sensor to be as well aligned to the wire's magnetic field as possible. So I want to try and hold it so that it's perfectly vertical like this. So right about there, looks like it's about right. Now you may be noticing that this value is jumping all over the place. So there's a feature of this program. You could hit a button on the calculator and it freezes the measurement. What I see is 0.15355. That's in millitesla. But the data table is asking for microtesla. So the way to convert that is just by multiplying by 1,000. And that's going to make the numbers easier to graph. So 153.55 is the first value that I'm going to record. Now, once again, you're going to be assigned your own value. So go ahead and in that sheet that includes the data in the Google Stream, go ahead and look up your value of magnetic field for 2 centimeters. Now I'm going to measure for 3 centimeters. So let me check this. I think I bumped it. Yes, I did. Okay, so 3 centimeters away. I'm going to try and align this as best as I can. Okay. Looks like right about there is good. Let me freeze the measurement. And looks like 0.124, which I can call 124.25 microteslas. So I recorded that for 3 centimeters. Again, you're going to look up your value and record it, so go ahead and do that now. All right, next, 4 centimeters. Looks like right about there. Okay, so 108.42. So again, go ahead and look up your magnetic field value assigned to you for 4 centimeters and copy it in your data table now. Let's move on to 5 centimeters. So 5 centimeters, right around there. Okay, so, okay, oops. 97.68. So go ahead and look up your 5 centimeter radius magnetic field value and copy it into your data table. By the way, I'm not putting units with these numbers because they're already at the top of the table for all those numbers. All right, 6 centimeters. Let me release this. Okay. Okay. So 91.82. Again, go ahead and look up your 6 centimeter magnetic field value and copy it into your data table now. Let's move on to 7 centimeters. Okay. 85.18. So there we are. So go ahead and look up your 7 centimeter value and record it in your data table now. 8 centimeters. Okay, looks like 80.1. So go ahead and get your data for 8 centimeters and copy it in your data table now. 9 centimeters. Okay, 75.41. Okay, so go ahead and get your 9 centimeter magnetic field value and copy it in your data table now. Okay, 10 centimeters. Uh-oh, I think my ruler moved a little bit. Let's try that again. Okay, 74.24. Okay, so go ahead and get the 10 centimeter value assigned to you and copy it in your data table now. Okay, one last one, 11 centimeters away. Okay, 72.09. Okay, so go ahead and look up in the sheet your 11 centimeter value and copy that into your data table now. All right, next thing we have to do is some data analysis. So first thing, notice that the magnetic field near the wire is large and then it gets smaller and smaller and it descends, but it does not descend to zero. And you should know why. Again, it's because the Earth itself is creating a magnetic field. So even as the wire's magnetic field is going to zero, the Earth's is still there. And so this would asymptotically approach the Earth's magnetic field value, okay? All right, so let me reconfigure the camera and help guide you through the data collection. At this point, we've done up to step 7. So we're up to step 8 here, and it says in step 8, in the space to the right, write an expression for the magnetic field caused only by the net current in the wire as a function of radius, assuming the wire is infinite in length. The basic formula for the magnetic field around an infinite wire. Go ahead and copy that down now. Step number 9, in the space to the right, write an expression for the net magnetic field caused by the net current in the wire and the downward component of the Earth's magnetic field. So write an expression for the net magnetic field of the wire and the Earth's downward component here. You could put like B Earth or something like that for the magnetic field of the Earth. So go ahead and write the formula for that now. Okay, number 11. Number 11 says, 10. By inspecting the expression generated in the previous step, determine a third column that can be calculated from your existing 2 columns that when plotted on the x-axis will generate a linear pattern. Then fill the third column with all of these values in decimal form. Make sure to add to the top of the column a label with units. So you're going to be doing something with one of these variables, either radius or the magnetic field, calculating a new set of values that will be plotted against the other. Put a label here of what it is you're calculating, as well as the units, and then fill in all these numbers with new values. Go ahead and do that now. Okay, so the next thing that you're going to do, number 11 says plot your data on the grid provided. Do not create any breaks in any axis. In other words, you're starting at 0, 0, and you're going even spacing along these axes. So then you're going to plot these data points, and I'll just, because I'm not going to be able to help you, I'll just tell you that it should look something like this. And I'm guessing the pattern, but you should see something like, and actually no, there's no value here. Okay, so it'll look something like this, some kind of pattern that looks pretty linear. I don't know if that looks linear, but it's supposed to be linear. And then step 12, and don't forget, you need something here, you need something here, you need something here as well. So make sure you do that. Okay, so maybe I'll create a pause here. Go ahead and set up your axes and plot your data points now. Okay, 12 says, construct a best fit line. Make sure that it extends to the y-axis of your grid. So take a straight edge, and again, you know about best fit lines. I don't need to tell you too much about it, but basically what you want to do, it's a little hard because the camera's in the way, but something like this, nice, crisp, oops, and then my ruler moved, but you're going to do a better job because you won't have the camera in the way, and you want this to extend from both extremes of the graph. Make sure it hits here. That's what the instructions say. Okay, so there we've got our best fit line. We're on to step 13 in the analysis. Calculate the slope of your best fit line. You will be scored on the degree to which your calculation minimizes random and systematic error. That means you're not using your data points at all. Okay, none of these points get used in your calculation. You're only picking 2 new points on the best fit line. You're also not picking 2 points close together like that. That maximizes the error. Pick 2 new points as far apart as possible. Maybe even the very beginning, very end would work, but calculate your slope here in this region, right? So slope equals change in y over change in x, and then pick your numbers and calculate, and don't forget the units there as well. So go ahead and do that now. Okay, so step 14, using the slope calculated in the previous step and any other relevant data, determine your experimental value of mu0 or the permeability of free space. So what you're going to do is, let me get the lights back on. Okay, so what you're going to do here is somehow you're going to use this slope value, and in the end you're going to have mu0 from the slope only. Okay, now the way you'll figure that out is from this equation here and your linearizing process. You'll think about what's on the y-axis, what's on the x-axis, and then from this equation, you should be able to see what the slope is in terms of mu0 as a formula. And then you'll have a numerical value. You set it equal to that, and you solve for mu0. So go ahead and do that now in this space. Okay, now 15, calculate the percent error between your experimental value of mu0 and the accepted value. As you know, the accepted value is 4 pi times 10 to the minus 7 Tesla meter over amp. Again, don't forget those units there, but do a percent error there. So go ahead and do that now. Okay, moving on. So step 16. Procedure for determining the net magnetic field of the Earth. Use a value from your best fit line to determine the downward component of the Earth's magnetic field. Looking back at your equation from step 9 may help you. So if you look back at this formula you made for the magnetic field around a wire, including the magnetic field of the Earth, you'll be able to see how the magnetic field of the Earth could be determined by some feature of this best fit line. Okay? So that's what you're going to do. You're going to look at, and that's only the downward component, by the way. So go ahead and look at this line and see if you could figure out the downward component of the Earth's magnetic field. Go ahead, do that now, and record it right here. in, of course, microteslas. Okay, so go ahead, do that now. Okay, 17. Using the value determined in step 16 and the inclination angle for the Earth's magnetic field determined in step 1, create a vector diagram of the Earth's net magnetic field. Draw the diagram roughly to scale and include properly labeled components with experimental values included if known. So here's some dotted lines, the horizontal direction, the vertical direction. Geographic north is over here. That means like geographic north. What do I mean? Well, you know, I don't want to say the North Pole, but basically like, all right, where Santa is, right? So up there, and this is the south, geographic south where Antarctica is. So based on that, draw a vector, one arrow. Maybe you think it goes like that or up like this. One arrow that represents the net magnetic field starting here and keeping in mind this dip angle that we measured earlier, minus 17.5. So yours will be something maybe like 18. Draw the arrow approximately to scale with the approximate correct angle here. So go ahead and draw the net magnetic field and the components. Somewhere in that diagram, this value is going to go either in one of the components or on the hypotenuse. That's for you to decide. So go ahead and create that vector diagram now. Okay, steps 18 and 19. Calculate the two other sides of the magnetic field vector diagram. It doesn't matter which side you calculate first. So there's two spaces, right? Because this is going to go either on one of the legs or the hypotenuse. That would leave two other things in the triangle to determine, here and here. So go ahead and calculate those other parts of the triangle in these two spaces, one for each. Go ahead and do that now. Okay, next one, step 19. Using the site here and the zip code of the high school, 10994, that's where I'm doing this experiment. Look up and record the net magnetic field of the Earth in this exact area. So go ahead on the web, using this website, record the net magnetic field here. Go ahead and do that now. And 20, calculate the percent error between the net magnetic field of the Earth as determined from your vector diagram, the experimental value, and the one looked up on the internet, the accepted value. So one of these is the experimental. This will be the accepted value. So go ahead and calculate that percent error now. Go ahead and do that now. Okay, so now we're done with one major part of this experiment, but there's another part that I want to do. This is going to be on a later day, but you know, you could continue on if you have time, because this lab is pretty long. But what we want to do is determine the validity of the long wire approximation formula that we wrote earlier in the lab. You saw the wire in the room. Can it be considered infinite? Does it satisfy the requirements? We're going to analyze and see if it can be considered infinite. So 22, on the diagram shown on your answer sheet, mark your approximate location during this experiment. Also on the diagram, record the total length of the straight portion of the wire that produced your magnetic fields, as well as the distance where you performed your experiment to either end of the wire. So what does that mean? So here's maybe I'll get a colored marker to highlight this a little bit more. So normally when we're in school, I set this wire up going all the way around the room so that all the students in the classroom could go along these various lab tables and perform the experiment. But I'm doing this by myself, so I decided to only set up a portion of the wire. So I did this portion right here. And then from here, the wire you know, when I move the camera, I'll show you. It kind of goes like this along the floor, and then here's the table with the power supply and the rest of the wire. And so that's the portion that's the straight portion. And I perform my experiment somewhere around here. So what I want to do is now take the tape measure out and measure the length of this wire, the straight part. Measure where I am. And then I'm going to do an analysis to calculate the magnetic field of an infinite wire, and then calculate the magnetic field of the actual wire, the finite length wire with the measurements, and see how different my values are to see if that formula for the net magnetic field is valid. So let me move the camera so I can make the measurements, length of the wire here, as well as these two distances. So as I just explained, the current came out of this power supply, you know, coiled around here, came along this wire that runs along the floor. I don't know if you could see that, but it comes up here and then sort of goes along this back table, and then it's pulled nice and tight. So this is my straight portion, starting here, going over the place where I took my data, continuing on, and then reaching right here. And this is the point where the straight portion ends, and then we got, you know, basically back to the power supply, we've got that loop. So what I'm going to do is measure the length. I think maybe it'd be easier here because I could hook onto that 2x4. If this will reach, there we go. Okay. So looks like I've got about 430 centimeters. In other words, 4.3 meters is the total length of the wire. Is that long enough to be infinite? That's what you're going to be calculating. So let me jot that down, 4.3 meters. Okay. Now, I wasn't at the center, so what I want to do is measure how far away I am from the end of the wire. So right here, my experiment was conducted at 244, well, that's enough significant figures, 244 centimeters from the end. In other words, 2.44 meters from that end. So I will go like this. Okay. Let me show you the measurements that I made. So right here, I hope you could see that. I've got a total length of the wire, 4.31 meters. And then from this end, 2.44 meters. Obviously, I could find this end by subtracting these two numbers. So I have all the measurements that I need. Again, you're going to look up in the Google Stream the sheet, and you're going to get your own two values here for the lengths, total length of the wire and how far from the end. So go ahead and do that now. Sketch them into this diagram to the best of your ability. All right, now what I'm going to do is take you through the data analysis. So let me reconfigure the camera one more time. Okay, I jumped ahead a little bit with the measurements. I skipped step 21. 21 says using the long wire approximation formula for the magnetic field of a wire, determine the net magnetic field 11 centimeters from the wire. Record all of the digits shown on the calculator screen. Do not round. And the reason why we're using the 11 centimeter distance is because the further you get from the wire, the less it seems infinite. The requirement is that the radius, the distance from the wire, has to be much less than the length. So the error becomes most pronounced. The wire looks least like an infinite wire the farthest we were away. So calculate the magnetic field using the basic formula for the infinite wire, 11 centimeters from the wire, using the current in the wire of the 7 strands from earlier, like the 10 amps or whatever it was. So use the basic formula, calculate the magnetic field here. Go ahead and do that now. Again, don't round off at all. Keep all the decimals because we want to see just how precise this is. So go ahead and do that now. Okay, we did 22 already with our measurements. This diagram is just here to help you if you want to draw like where you are in your integration, but basically we're going to be at this point here, and what we're going to do in step 23 is we're going to, well, it says using the Biot-Savart law, determine the net magnetic field caused by this wire segment, not the infinite, the actual magnetic field. Your calculation may take up a significant amount of space, so you should start your calculation all the way at the top left portion of the space provided. Leave no margins. A lot of students see a big space like that and they say, oh, okay, let me start No, start way up here at the top because again, you're going to need a lot of space for this. Okay, so if you find that there's not enough space to perform your calculation, you may attach another sheet to your lab analysis. Also, when entering your calculation into your calculator, do not round between steps. And again, record all the digits shown on the calculator screen. So when we're all done down here, you'll have B equals all your decimals, Teslas. Or you could convert to micro Teslas, whatever you want, but basically the same units that you're using up here. So go ahead and do that calculation. Biot-Savart law, calculate now. Okay, the last thing, 24, is calculate the percent error between step 21 and 23. Since the step 21 is the result is an approximation using this formula here. It's not truly an infinite wire. This is the more accurate one, the Biot-Savart law. So this will be the accepted value. That's what this is saying. So when you're all done here, you'll have a percent error to see just how valid our assumption was that this wire was infinite. Go ahead and calculate that percent error now. Okay, so that's that page. Okay, the next thing, questions. According, it looks like I have quite a few typos. I got to go through this carefully. According to the results of the last steps in the procedure, did using the expression for the magnetic field around a long infinite wire create a significant error, or was it insignificant? Like in other words, if we had 15% error, well, that's a significant error. So you would say, yes, it was significant. But if we had like a 0.1 or 0.01 or some small percent error, then you would say no, obviously. So that's, answer that question here. Go ahead and do that now. 26. The current in the wire used in this lab was not produced by a solid conductor. A multi-strand conductor was used to loop a small current around 7 times in order to multiply the current. I mentioned that earlier. But whether you use Ampere's law or Biot-Savart law, the current was assumed to be symmetrically distributed around a single conductor. Was the multi-strand feature significant enough to introduce a sizable error, 5% or more, between your measured magnetic field and field calculated from theory? Defend your hypothesis. So maybe you're starting somewhere around here. I don't know. It depends on how much space you needed for the previous question. So basically, we assumed the wire had the current evenly spread across, and then we could use mu equals 2 pi r, like this, or the Biot-Savart law. But the reality is we had 7 wires. 1, 2, oops, I think I need to draw these a little bit bigger. 1, 2, 3, 4, 5, 6, 7 wires packed in like this. The question is asking, does this make a significant error compared to this, that the current is 7 conductors? Don't look this up on the internet. Sometimes people talk about skin currents, don't look it up. Just think about, do you think if you found the magnetic field from all 7 of these wires at this point, and you actually calculated from the 7 wires, would it be much different than calculating of 1 wire with the current evenly spread out like that? It's just basically like just thinking about reason and how you would do a vector sum of the net magnetic fields. So go ahead and just make a reasonable argument one way or the other here. Go ahead and do that now. Okay, 27. There was another flaw in the reasoning we used in generating even the Biot-Savart expression for the net magnetic field. Explain what that was and then defend an opinion of whether or not that error significantly impacted your measurements. The hint I'll give you for 27, there's another error that something we did not factor in. This is the circuit I used in this experiment. Can you think of some other influence that contributed to the magnetic field here, other than this idea of an infinite wire or even a segment by Biot-Savart law? Think about the circuit, how it actually worked, and tell me what the other factor is, or factors, and whether or not you think they contributed significantly to the magnetic field here in the vicinity of my experiment. So go ahead and answer that question 27 now. So that was the last question of the lab. That concludes our experiment, determining the permeability of space using a long wire. I hope you enjoyed the data collection. I hope you enjoyed the data analysis. I'll see you in the next physics video.